In section 10.4, we discuss the strength of acids and bases. So strong acids are all covalent compounds, that is, they exist as discrete molecules, that when dissolved in water, completely are converted into ions. In particular, they will form one or more hydronium ions and an anion. And this is illustrated nicely by what happens when hydrogen chloride is dissolved in water. The acid donates a proton to water, leaving the chloride anion and creating the hydronium ion. So classic strong acids would be things like hydrobromic acid, hydrochloric acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. And you see this happening in each case. A proton transferred from the acid to the water, and it always generates the hydronium ion and an anion. And that's true for all of the examples given there. So the acid is completely converted into ions. There are two common classes of strong acids. There are what we call binary acids, and the binary acids that are strong are hydrochloric acid, hydrobromic acid, hydroiodic acid. Now, HAF is also a binary acid, but it is not strong. This class of acids are also referred to as hydrohalic acids. Oxygen-containing acids, or what are often described as oxoacids, are strong if the number of oxygen atoms in the formula is 2 or more than the number of hydrogen atoms. So let's just have a look here. So in this acid here, it's called sulfuric acid. We have 4 oxygen atoms, which is 2 more than the number of hydrogen atoms. So this guy is strong. In this acid here, it's called nitric acid. We have 3 oxygen atoms, which again is 2 more than the number of hydrogen atoms, because you have 1 hydrogen atom in this case. So therefore, this is a strong acid. This final acid is called perchloric acid. We have 1 hydrogen atom, and we have 4 oxygen atoms, so we have 3 more oxygens. So that 3 is, bigger than 2, so that acid is strong. The acid dissociation reaction may not be complete. That is, it might be an equilibrium reaction. So we can characterize this by an equilibrium constant, and we call the equilibrium constant describing the dissociation of an acid Ka. So how do we write it? Well, it's products over reactants. But you'll note that we omit the term for liquid water. And this is common throughout, that we omit liquid water when it's a solvent, because the concentration of the liquid water is very, very high, so it remains approximately constant regardless of what's happening in the reaction. So when we write a Ka expression for an acid, we omit the term for water and we just do products over reactants. So Ka is sometimes called the acid dissociation constant. So if you hear that term, that's what they're talking about. And what's important to recognize is that strong acids will have Kas that are much, much bigger than 1. And so we'll tend not to use the equilibrium arrow in that case, but rather just write a conventional arrow pointing to the right. Now, weak acids have Kas a lot less than 1 and are mostly unionized in solution. So for a typical weak acid, you might have, say, 99% of the acid remaining intact and only 1% of it being converted to ions. For that reason, we're going to use an equilibrium arrow when we're talking about the dissociation of a weak acid. So common weak acids include hydrofluoric acid, which we mentioned previously as not being strong, Oxoacids that don't have enough oxygen to be strong, so for example, if we only have one more oxygen atom than hydrogens, or if we have an equal number of oxygen and hydrogens, so this one here is nitrous acid, we only have one more oxygen than hydrogen in this case, so it doesn't meet the criteria for being strong. And a very common class of weak acids that are important in biochemistry are carboxylic acids. And you can recognize carboxylic acids because they all have this ending on their formula COOH. So they'll have some kind of group and then it'll end COOH. When a base is dissolved in water, the water will function as an acid, generating the conjugate acid of our base and the hydroxide anion. And this can also be characterized by an equilibrium constant, which we're going to call Kb because it's a base. And the same thing applies for Kb. We're going to do products over reactants, but we're going to be leaving out the term for the water. Now just remember that when we write the formula of something inside square brackets like that, what we're really saying is the molarity or the concentration of whatever is in the square brackets. So weak bases, which are normally molecular species, will have Kb's a lot less than 1, and strong bases, which are normally ionic species, will have Kb much, much greater than 1. An interesting property of water is that about 6 in every 100 million water molecules will ionize or fall apart to form hydrogen ions and hydroxide anions. And this process is referred to as the autoionization of water, and we can write an equilibrium constant describing it. So it's similar to a Ka. We're going to do products over reactants, but we're going to omit the concentration of the solvent. So the autoionization constant of water, the equilibrium constant describing this process, is normally called Kw, and so Kw will equal the hydroxide ion concentration multiplied by the hydrogen ion concentration. Now in pure water, the hydroxide ion concentration and the hydrogen ion concentration are equal, and both are found to be 1 by 10 to the minus 7 moles per liter. So that means that Kw is 1 by 10 to the minus 7 times 1 by 10 to the minus 7, or 1 by 10 to the minus 14. Now it turns out that for any aqueous solution, Kw always equals 1 by 10 to the minus 14 at 25 degrees Celsius. In a neutral solution, hydrogen ion concentration always equals hydroxide ion concentration and is 1 by 10 to the minus 7 moles per liter. When we add an acid, remember that the acid functions to increase hydrogen ion concentration. So now the concentration of the H plus will be greater than 1 by 10 to the minus 7. But because the product of hydrogen ion concentration and hydroxide ion concentration must always equal 1 by 10 to the minus 14, that means that the hydroxide ion concentration now is less than 1 by 10 to the minus 7. In a basic solution, remember that bases act to increase hydroxide ion concentration. The hydroxide ion concentration is greater than what we find in a neutral solution. Again, because the product of the hydrogen ion concentration and the hydroxide ion concentration always has to equal 1 by 10 to the minus 14, that must mean that the hydrogen ion concentration in a basic solution, it must be less than 1 by 10 to the minus 7. So what we're really saying is that if H plus concentration goes up, hydroxide ion concentration must go down, and if hydroxide ion concentration goes up, you guessed it, hydrogen ion concentration must go down. And the reason being, when you multiply the two concentrations together, they always have to equal 1 by 10 to the minus 14. So dealing with molarities can be complicated because we have such a wide range of concentrations that we're going to be working with. So it's common to specify the pH of an aqueous solution, and the pH is simply the negative log of the hydrogen ion concentration, or the hydronium ion concentration more correctly. So it should be noted that hydronium ion concentration and H plus concentration are always equal. So a neutral solution has a pH of 7. Solutions that are basic have a pH that is greater than 7, and solutions that are acidic have a pH that is less than 7. There's no lower or upper limit to the pH scale, but it's often indicated between 0 and 14 because that's a common range that we're going to encounter. You'll notice that a lot of cleaning substances are basic, and a lot of the things that we eat are quite acidic. That's really because our stomach is full of hydrochloric acid, so we've adapted to tolerate acid fairly well in our mouth and in our throat, etc. So how does one calculate a pH? Well, it's pretty easy. What you're going to put into your calculator is just the negative log of the number, and that will return the number. Now, that's pretty easy, but you might have to look up where the log button is on your calculator. So you're going to do negative, not subtract, but the negative symbol, 2.5 by 10 to the minus 11. We'll put that into the calculator. Go, and last but not least, negative log 4.7 by 10 to the minus 9. Okay, so in the first example here, the H plus concentration was greater than 10 to the minus 7 molar. So we had an acidic solution, and that's indicated by the pH that is less than 7. In these two examples, in both cases, the concentration of H plus is less than 10 to the minus 7 molar. So we know that we have a basic solution, and in each case we observed that the pH was greater than 7. Okay, and that concludes our section on the strengths of acids and bases.